Okay, so let's get started. Thank you very much for this great opportunity of the presentation. I'm Ryotaro. I'm a graduate student in Minda's group. Minda is that's organizer. Today I want to talk about this machine learning assisted study of the quantum material property and quantum material discovery. Today, the machine learning is becoming a very hot, intense topic. The material matters, not the exception. In general, this kind of study, some start from the small molecule that have the very large data set of the HCN, very simple, like the well-known atomic species, and also like the proteins that is like also made of the 20 kind of very simple atom type, the very small number of the kind of the atomic amino acid. And I think many of you know that today the Nobel Prize in Chemistry was about the protein structure prediction and the design. Yeah, it's a kind of the hot topic. Furthermore, today that this machine learning for crystal is becoming more and more hot topic, including the condensed matter. Even though these all of them are common, is that everything is made up of the atoms and structured matter, but this small molecule protein crystal have the different nature in terms of the periodicity and the symmetry, etc. For this kind of the matter modeling, we often use the representation called the graph representation or graph neural network. What it does is to represent this atom as a node and this atom and atom interaction as edges. We build this kind of the graph architecture and let this model learn the relationship of the geometry and atomic species. Recently, there is a more advanced version of the method called the equivariant neural network that is to take the symmetry of the object into account. What the symmetry means that if the input, like the molecule or object is rotated, some invariant properties, such as some spectra of the XRD, remain the same, but for example, some orientation-dependent property, like the interatomic forces, rotate accordingly. This makes this the data efficient and that could make the training of the model for applicable for many kind of the objects. Especially for the quantum material community, the structure property relationship is one of the important study for using this AI-based study. What I mean is given the structure, it's important to know what kind of the structure gives what kind of property. This example is a phonon dispersion, or other is like the band gap, or more hopefully the electronic band structure, or magnetic order, etc. And also in the very long, some inverse design could be the very important. Another project that is we want to have some material with a very large band gap. Based on this condition, we'd like to generate the material structure. What kind of material atoms organize which structure? Yeah, I want to introduce several of the research of these two aspects. And first, this property prediction. I want to talk about the two projects. It's about the thermal property prediction and the optical property prediction. And first, the thermal property prediction as a motivation is to achieve the more efficient management of the thermal energy. It's well known that most of the electricity generated by the power plant is finally lost as waste heat energy. So in order to reduce this loss, we need to find the efficient way of to manage the heat energy. It means that we should use the material that can insulate or transmit in each in each scenario. in our group, we have applied the graph neural network to predict the phonon density of state. This has enabled us to screen the material, for example, the material which has the high heat capacity. So this material help us to find the material in terms of the thermal management. However, this is not enough. We to find the more to do the more thorough screening of the material. We need the more detailed information of the thermal property. So how can we go further than that? To make this kind of prediction better, we need to consider how we can improve this machine learning model architecture. To consider that approach, here this is a very conventional method of the GNN. That is we regard the atom as a node and this atom interaction as an edge. Each atom has a one node feature. Each by doing the method called the graph convolution, we optimize this feature so that this output becomes the property we want. However, this is not this conventional method has not deal with all the cases of the material property. To make this method more flexible, we apply the method called the virtual node. That is we put some if we have some crystal, we add some atom that doesn't exist, but it's useful in terms of the changing or optimizing the dimension of the output. So I skipped the very detail of the method, but this method could enable us to model given the material structure, we can predict the phonon band structure based on the dynamical matrix. It means that this method could do the prediction that is more based on the more principle of the phonon calculation. Our property prediction work is not limited to this, but we have another work for the optical property prediction that we call the GNN opt. What it does, the one unique point of this method is it not only we use the GNN, but also this method enables us to find what kind of the material feature is important. We usually for the phonon prediction, we use the atomic mass as each other input feature of each atom. However, for this optical property, we don't know which feature actually matters. So we implemented a new method called the universal embedding that can automatically find which aspect of the material atoms, like the atomic mass or electronegativity or atomic radius. And finally, we could find that the atomic radius takes a very important role in this optical property prediction. Here's this output of the optical property prediction. This is overlaying the color spectrum is the prediction. Overlaid with this black ground truth spectrum. That we can see that most of the spectrum is very overlapping with ground truth, showing its strength in the prediction. And furthermore, the GNN opt have the more application, such as it can find which material is expected to be the efficient material for the solar energy solar panel. It can also find using this predicted optical spectrum, we can find that which material could be the more like the quantum material. That is also verified by the DFT calculation. So far we have introduced the property prediction method, but the machine learning approach is not limited to that. We can apply the inverse design using the GNN. That is how we can discover the new material that have the potential application. So recently, like the not very recent, but last year, DeepMind have released the one work that is called Genome. That is to use the generative method to it released many new material structure that doesn't have existed in the previous material database. That has expanded the number of the material which human has experimentally synthesized to the many scale. So this by doing this kind of generative approach, we can find a new material candidate. However, this kind of it's a kind of a random search, so it's not very efficient to find the material which we want in terms of the further more theory or experimental study. One of the some demanded material to discover is called the quantum spin liquid. That is the magnetic atom forming some geometric pattern like the triangular or honeycomb and Kagome lattice. That helps depending on this geometry, that can help the magnetic disorder even at the low temperature, and that could be said to be some new potential candidate for the quantum computing application. So we would like to find more candidates, but since this kind of material is very scarce compared to the other more general inorganic crystal, it's not efficient to directly apply the generative model to do it. Considering that, we do we consider the kind of top-down approach that to discover the material that helps the triangular honeycomb and Kagome that's formed by the magnetic atom. Give this as a structural condition, we explore how we can find the new material. And the approach we took is called a conditional generation. That is called in-painting in the image generation. That is if there is a woman picture wearing the mask, we can guess what the face under the mask is. We can apply this kind of method to find, considering that this geometric Kagome or triangular lattice is this non-image part, and other field atom is something below the mask. We can feel apply this same method as the image generation to find the material that is have this geometric pattern and enough stability. So here's the very overview of our methodology. The top part shows what kind of the structure we give as a constraint, and the bottom is how we apply this method conditioning iteratively. This is how the material is generated through what we call the denoising process. We can see that triangular and honeycomb lattice is finally generated. However, we need to do some screening so that, or we can select only some stable material as a candidate for the next, the experimental or more heavy, the more detailed DFT calculation. So we apply this kind of layered filtering method so that we can screen the large candidate, and finally we can get a very small subset for the next study. This is just a subset of the material we get. Have the triangular and honeycomb and Kagome. That is proved to be stable by the DFT. Not only this kind of the three geometric pattern, but we can apply for the other geometric pattern called the Archimedean lattice. We can find the material candidate. And furthermore, we apply the constraint to this Lib lattice material that is said to present the flat band structure. We could actually observe the flat band structure in the DFT result. we store the all generated material as a database, and I hope potentially becomes some material further material study. Yeah, this is a summary we have. We apply the predictive model and the generative model, but machine learning itself is not does not conclude all of this material condensed matter study. The collaboration, the joint study of the experimental and the more theoretical study will be very important. But I think that machine learning in the condensed matter could be more can advance much further in the near future. Okay, so this is all the presentation. Thank you so much.
Yeah, you mentioned at the beginning thermal management.
Mhm.
So I thought you were going to give like thermoelectric
Mhm.
merit.
Mhm.
Is there any like prediction for new materials
Uh,
domain? I mean, people are always looking for increasing that value.
yeah, actually, our group has the member, one of the previous business scholar, was discussing about that. I think right now we don't have the solution, but my guess is that is kind of the reinforcement learning. We have some several parameters that give the ZT, and let the some machine learning method to learn how we can tune each parameter so that this ZT becomes the maximum. But yeah, there is some constraint in the tuning the parameter. So yeah, that could be the. I don't have the very direct answer, but could be the
I mean, are there any
interesting.
specific successes that you can point to in like any domain? Like you want to optimize this property, and machine learning gave us a new material that hasn't been discovered by just DFT or experimental exploration. Like, do we have those key successes yet?
Actually, we haven't included, but kind of partially yes. There is for this generative model work, our collaborator has worked on some experimental verification. Not exactly the same, but we can find some competing phase crystal that is experimental show to be the magnetic property.
I had a question about the ground truth that you used for
Uh-huh.
these predictions. Is it based on like experimental raw data from similar crystal structures, or are you using some sort of model?
Usually, it's data from DFT. It's the reason is mostly it's the number of the data, but yeah, since DFT and experimental result could be different, so one possible approach is train by the DFT and fine tune or what we call the transfer learning to further fine tune for the experimental cases.
Yeah, I wonder if there is a artificial effect in the structure. I wonder if the GNN you mentioned can work.
Defect. This defect could be I think, still challenging, but could be some next potential project. The defects difficulty is if the crystal is perfectly periodic, we can represent. We don't need. We can just represent the one unit cell. But if there is a defect, we cannot represent the crystal with single crystal unit cell. So we need to consider supercell, but that can make the computation getting heavier.
When doing the Follon, when doing the Follon thing, so actually using DFT to calculate the Follon thing, if there is a defect, it's very hard to get the data, right?
Yeah, yes, it's still difficult in machine learning too, but considering the machine learning is light, some computation of the machine learning is lighter, less heavy than the DFT, so that is still manageable. It's not perfect.